Welcome back to the next lecture. So in this lecture, first we will know why we are going to study linear algebra. This is a very important question because you have already uh, done the linear algebra in your 10 plus 2 class or high school. But the important thing is that what am I going to do something different, and how am I going to do the things in a different way or in a different setup which requires to study linear algebra further. Right. So let us give a very small motivation here. I'm going to discuss about 2 by 2 system. So if you see here, 2x plus y equal to 5, equation number 1, and x minus y equal to 1, second equation. Okay. Now if you see, this is the two equations which has been plotted in xy plane by different color, because green one is the line which is equation 2, and then red one is the line for the equation, presenting the line for equation 1, right? So they are meeting together at one point, and that point is 2 comma 1. So it means that this system has solution x equal to 2 and y equal to 1, right? So which is just simply solving each row individually. If I'm going to write this system into a matrix form, A is the coefficient matrix and B is the right hand side. So what you have done till 10 plus 2 is just the row picture. Row picture means each individual row, like equation number 1 and equation number 2, you are solving, and you are going to solve x equal to something in terms of y, and then you are going to substitute y in terms of x, and then you are going to get x and y value together, right? So you are solving first, or in other word, you are drawing this line first, and then another line, row 2, you are drawing another line, and they are meeting at some point, whether they are intersecting or not, depending upon the situation, you are going to define the solution. Okay. So now here, what you have done till now is row picture, right? Now I'm going to do the same problem with different way. Like if you see the same equations, I'm going to use column picture. Column picture means each column of A represent a vector, right? So if you see, this is the column, right? Column 1, column 2, let us say C1, C2. Okay, so column 1 is 2 comma 1, and column 2 is 1 comma minus 1, right? And we are going to say these are the vector v1 and v2. So now if you see in xy plane, and if you see first vector from origin 2 comma 1, so it runs two distance and then one distance in y-axis. So this is the vector. Okay. Now the question is, in row picture, in spite of row picture, in column picture, what's the question? How much times of x with this vector plus how much times of y with another vector produce the right hand side, right? It means that how much quantity of x vector plus much quantity of y vector produces the right hand side, that is 5 comma 1, is my question, right? It means that vector v1 and v2 is going to form a linear combinations, right? So how much times of x with this vector with linear combination of how much times of y with another vector. So the linear combination comes into the picture, right? We are going to introduce linear combinations, and we are discussing with in terms of vectors only, right? So now if you see here, as you have seen already, the solutions are 2 comma 1. So now what does it mean? X means 2 times of the original vector. So the original vector is this, then 2 times means it stretched towards one more time. This is 2 comma 1. So 2 comma 1 after multiplying 2 means 4 comma 2. So this is the point this is the vector, right? Now plus 1 comma minus 1. 1 comma minus 1, if you look at this equation, right? 1 comma minus 1. 1 from x-axis minus 1 from minus negative y-axis, right? If it is this your x-axis and if this is y-axis, so 1 comma minus 1, negative y and negative x, right? So if you see here, 1 times of that 1 comma minus 1 vector. So what exactly it had happened if you translate this vector using parallelogram law property, then this is the your addition vector, right? And this is nothing but 5 comma 1, right? Now the question is what we have learned here, in spite of row picture, we are going to work with column picture, right? And how am I going to get some more help while doing this stuff? So if you look at it, suppose if you are dealing with three equations and three unknowns, 3 by 3 system, right? And if I represent x, y, and z, right? This is, you can assume as a blackboard plane, xy in a blackboard plane, right? X and y in blackboard plane, and z is perpendicular to the blackboard, right? So now if you see here in this picture, suppose you have three equations, three unknown, and three equations means here if you see the two variable represent line, right? Then three variable represents plane. So now if I'm going to see first plane, second plane, another plane, so it is very difficult, to know which plane is intersecting to which plane, and the simultaneous solution will be the common solution for this system. So it means that the row picture is going to make life measurable when we are going to move higher dimension, right? Let's say this is for 3 dimension, right? 3 dimension or 4 dimension or more and more. So it's very difficult, right, to see from the row picture, right, intersection, or even it is harder for higher dimension greater than or equal to 4. So in that case, column picture helps us a lot. Column picture means just simply you are going to look this space, right? And then vector, this is another vector, this is another vector. How many linear combination of these, how many linear combination of this produces linear combination of this? Then it is very easy to visualize with the help of column picture rather than row picture. That's what we are moving that's what we are going to study the linear algebra in a very abstract manner. Okay. So now what we are going to look in this lecture, we are going to see the row space. Row space means row of the coefficient matrix basically, right? And which forms a space, okay? So now let us see what is the row space. So the space Rn, we call sometimes n vectors, right? N vector x. N vector x means x can be of the form of x1, x2, and so on, n tuples. And we are denoted as ordered n tuple of real numbers, right? The numbers x1, x2, and so on xn are referred as the coordinates or components of the n vector. Like for example, if r2, so if I say x comma y, right? So my vector representation is x comma y. It means this is x coordinate, this is y coordinate. So how much x you are running, how much y you are running, and then make a common point, right? So each x, y are coordinate. So if we are going to run in n dimensions, so we are representing with the variable x1, x2, x3, x1, xn. Okay. And sometimes we are also calling as the components. Okay. So it's your wish, whatever you are going to like, either coordinates or components, all are same. So now Rn the space of all n vectors, right? Like for example, R2 is the space of all the vectors. Similarly, Rn is the space of all n vector. So Rn is also referred as the n-dimensional Euclidean space, right? So now when we say equality of n vectors. When we say two vectors are equal, if their components are equal, right? Each components are equal. X1 equal to y1, x2 equal to y2, xn equal to yn, then we will say each two vectors are equal, right? Xi equal to yi for all I equal to 1 to n. Now, when we call it as a vector is zero vector, in n vector, zero vector means each component is zero. Each component is zero, right? Of all whose coordinates are equal to zero, called zero vector and denoted by zero arrow that represents zero. Rather than zero, simply if I write zero, it means that this is a scalar, right? But if I write this, then this is zero vector. So this is the notation we have to follow. Okay. In the books, several books, if you see, this is denoted as bold letter zero for writing zero vector, or origin we can say. Now addition of vectors. How am I going to add two vectors? So if two n vectors are there, let's say x and y, they can be added component wise, x1 plus y1, x2 plus y2, xn plus yn, and so on, right? So sum of the vector will be x plus y, x1 plus y1 plus x2 plus y2, and so on, xn plus yn, right? This is the sum of the vectors. Okay, example, if you see 3 comma 2 plus 2 comma 5. So what is the component wise addition? 3 plus 2 5 and 2 plus 5 7. So this is the component wise vector addition. Okay, now let us see multiplication of an n vector by a scalar. So this is very important, real scalars. So we can multiply an n vector by a real number, often called a scalar. Okay, so if x is a n vector and alpha is any real number, then alpha times of x is nothing but alpha gets multiplied to each component, right? Now we can see some property easily. Alpha times of x plus y equal to alpha x plus alpha y. Alpha plus beta times of x is equal to alpha x into beta x, right? And alpha beta x equal to alpha times beta x. 1 into x equal to x. Alpha into 0 vector is 0. Scalar 0 into x equal to 0 vector, because each component gets multiplied by 0. So it produces a 0 vector. Alpha into x is 0. Either alpha is 0 or x is 0. If you see from here, right? X is a 0 vector or alpha is scalar is 0. Then product will be 0, right? So now as you have seen linear combination already with the column picture, so we are going to be motivated by that and we are going to extend our idea into the k dimension, right? Or in general we can say n dimension. So let x1, x2, xn and xk be vectors, okay? And alpha 1, alpha 2 and alpha k be scalars. Then the vector alpha 1 x1 plus alpha 2 x2 and so on alpha k xk, that can also be written as in a compact notation I equal to 1 to k alpha I x I runs from 1 to k. This is a compact notation in summation form. And this referred as finite linear combination because k is finite, right? Finite linear combination of vector x1, x2, xn. Okay. So now the question, let us see one example. Let I 1 0 0, j 0 1 0, k 0 0 1 be the three vectors. Then the three vector 2 3 4 can be written as the linear combination of these three vectors, right? If you see the specialty of this three vector in 3D, this is 1 comma 0 comma 0, this is 0 comma 1 comma 0, and this is 0 comma 0 comma 1. So this is x-axis, this is y-axis, this is z-axis, and this has a special name I, and this is j, and this is k, right? Unit vector actually, right? So we can say unit vector cap. Okay. So now if you see this, these three vectors are very important actually in the R3, right? These three vector, any vector if you pick up in the 3D space, right? Any vector, then every vector can be written as the linear combination of these three vectors. And later we will see that these three vectors are nothing but the basis of the R3 vector space, right? We will see later. Okay, so now 2, 3, 4 can be written as the linear combination of this. So as I mentioned, every vector can be written as in the form of a linear combination of these three ijk vectors. So now if you see here, 250 is a linear combination of I and j only because j component is 0, right? So 250 can be written as the linear combination 2 times of I plus 5 times of j. Now let us see the problem. How to solve the problem? So the question is like that. Is the vector x, this is the three vector actually, a linear combination of the vectors a, a1, 2, 4, 2, 1, 4, a2, 1, minus 1, 3, and a3, 3, 2, 5. This is now my question. So solution. What does it mean? X can be written as the linear combination of alpha into a1 plus alpha beta into a2 plus gamma into a3. So alpha, beta, gammas are scalars or real numbers. Okay. So now when we write these vectors, so 5, 9, 5 can be written as alpha times of this a1 vector plus beta times of a2 vector plus gamma times of a3 vector. Okay. Then now when you equate this equation, as you know, the two vectors are equal, left hand side, right hand sides are equal, provided their components are equal. Okay. So now what we are going to do, 2 alpha, we are going to write 2 alpha, alpha, 4 alpha plus beta minus beta and 3 beta, second vector, plus 3 gamma plus 3 gamma, 2 gamma and 5 gamma. Right. Now the question is, I'm going to add addition will be only possible with a component wise. So what had happened, 2 alpha plus beta plus 3 gamma, right? And this will be the first component of the right hand side vector, which is equal to the first component of the first vector in the left hand side. It means that this will produce an equation because of the property of equality of two vectors. Okay. Similarly, second component, all the sum will be equal to the right hand side second component of the first vector, and similarly the third vector. So if you see, we got a system ax equal to beta I, and now the job is to solve this system, right? If this system has solution, it means that this vector can be written as a linear combination of the preceding vector of these three vectors. If this system has no solution or solution, only two cases will happen. Either solution exists or no solution, right? So if solution exists, then this vector can be written as a linear combination of it. If no solution exists, so this will not be written as a linear combination of the three vectors, right? It means that this vector is not in the row space of the given matrix. Okay. So now you know, the previously we have done in several videos Gauss-Jordan methods, and many times we are doing it again and again. So you can apply Gauss-Jordan method for solving the value of alpha, beta and gamma. So let us write the augmented matrix, just coefficient of A matrix, augmented B, right? This is the augmented matrix. Now all the entries and then coefficient of the right hand side we are writing. Since in Gauss Jordan what we want always 1 to the first place, right? First coefficient. So either you have a two choice, either you divide this equation by 2, first row, or else you swap the first row, the another row, right? R1 changes to R2. So this is the operation has been applied to interchange the row. Now I got pivot entry as 1, and the next job is to make the 0 on the same column, right? Make the 0 below the pivot entry. So to make the 0, if I get it multiplied 2 times of the R1 and then subtract it from R2, then I'm going to get 0 here. And if I'm going to multiply by 4 times in first equation and subtract it from R3, then I'm going to get 0 here, right? So this is a simple elementary row operation which I'm going to do it here. So now the reduced matrix is 1 0 0. So now row 1 job is over. This column 1 job is over. Nothing to do with column 1 now. Now we have to move to the next column and lower row. Next column lower row is having non-zero entry. Yes, we can make it as pivot entry as unit element, and then we can perform 0 below the this row, row, right? Pivot entry. So now if you see, we have to divide 1 by 3 to R2 to get it 1, right? And then now you subtract 7 times of R1 to get this element as 0. Okay. So in Gauss Jordan method, first we do triangularization and then we start from the rightmost column of the augmented matrix after triangularization, and then we keep making zeros above the pivot entries. Okay. So now if you see, after solving this, we got 0 here, 0 0 here. So this is in the triangular form. So now if I have to get this element is non-zero. So we can multiply by minus 3 by 2 to R3, right? This is the third column basically. So this is R3 row. Okay. So make some correction. So R3 then which become 1, and now once this is 1, so I got the 1 entry here, and then the job is to make 0 above from the rightmost corner. Rightmost corner means this side. We are moving this side and this side. So here 1, and then we have to make 0 here and 0 here using suitable elementary row operation. If I multiply 2 times of R3, so it becomes 2, and then subtract from R1. That will produce 0 here and remaining entries. And similarly, we have to multiply 1 by 3 to R3 and add to the R2. So the final matrix is for this column is all the zeros you have made. And then now finally, what am I going to do is I have to make the 0 to the above the pivot entry. So this 0 I have to make. What I have to do? R1 plus R2. So simply I have added R1 plus R2. So what had happened? 7 minus 4 becomes 3, and 0 minus 0, 0 plus 0 becomes 0, and 1 minus 1 becomes 0, and 0 plus 1 becomes 0. So 1. So now this is the final matrix I got. So if you see here, every column has pivot entry, right? And the column, the rank of this A matrix, rank of A is equal to 3. Number of unknowns alpha, beta, gamma are 3, right? 3 variables. And rank of A augmented matrix or A augmented B is equal to 3. Then in that case, R is equal, this is we are representing S in the previous lecture, and this is R. So, and this is represented as N. So R is equal to S and this is equal to N. So it means unique solution. unique solution exists. Okay, then the advantage of Gauss Jordan is a direct read of solution. We can read solution directly. So x equal to 3, it means alpha equal to 3, beta equal to -4, and gamma equal to 1, right? Hence, what is the conclusion? Hence, this vector belongs to the row space of A, and that is going to be 3 times plus -4 times and plus 1 times, right? This is how we can solve the given system. Now let us introduce define the definition. A matrix of m by n size, then its row R1, R2, and so on Rn are the n vectors and which belongs to Rn, right? Each vector has n components, so they belongs to Rn. So this is row 1, row 2, and so on, row n. Okay. So the set of finite linear combinations, the set of finite linear combinations of row vectors is called the row space of A, right? This is the definition. Okay. Thus, a typical element of row space of the matrix will be of like this: alpha 1 R1 plus alpha 2 R2 and so on, linear combination of row vectors for some scalars alpha 1, alpha 2, alpha n, and so on. So definition of row space means the set of all finite linear combinations of row vector is called the row space of the given matrix. Okay, so if you see here in this problem, set of all linear combination, set of all linear combination, or we can say that set of linear combinations of the row space, row vectors. So this is the row vector of row of original matrix. So if you see for some scalars alpha, beta, gamma, we got this vector. It means that this vector is in the row space of A. Okay, set of all finite linear combinations of these row vectors is called the row space of A, right? So now here some scalars is important. Now here let us do the next problem. Determine whether the 3 vector, this is in the row space of the matrix. Matrix is given by this. Now this time they have given the matrix. So you have to construct this into a linear combination. This into alpha times of the first row, beta times of the second row, and gamma times of the third row. Now again use the same vector addition and scalar multiplication and equality of the two vectors. Then you will produce a system, right? And then use the same Gauss-Jordan method as before to find the solution for alpha, beta, gamma. If so, then your vector is given in the row space. If not, then this vector is not belongs to the row space. Okay. So now we have to solve the system. Solving the linear system A transpose X equal to B because of the fact that A was given. So if you see here, this becomes this row becomes column. So what is A transpose here? A transpose is nothing but 3 1 1 2 minus 1 5 and -4 -3 and 3, A transpose, right? When you solve the system, you see here 3 1 1 coefficient matrix. So basically, in spite of solving Ax equal to B, we are solving A transpose X equal to B, right? Just a representation of, symbolical representation. Otherwise, the taste and smell all are same. Okay. So now if you see here, solving this system and then transpose of the matrix and then find the solution. So X is alpha, beta, gamma, B is this. Then now we are going to use make the problem. So start with the augmented matrix. I'm representing A given B as usual notation. But if you want to write in the reference of A, you can write A transpose given B also. That's fine. Okay. So now this matrix, if you see, I want 1. So I will swap the first row by second row to get first element as 1. Okay. And then use the elementary row operation, these two elementary row operation to get 0 below the pivot entry. Once this pivot entry is done 0 0, then I have to target next row, next column and lower row. Next column lower row entry is non-zero. We have to make it 1 by suitable elementary row operation after multiplying 1 by 5 times to R2 vector. So now this is identity, this is unit element, which is called a pivot element. Now we have to make it 0 to this using suitable elementary row operation, and we got this 0, right? Now what had happened, we have to move to the third column lower row. So third column lower row is already 0. It means that we are not going to get pivot in this column. No pivot, no pivot, no pivot. What does it mean? If you see the rank of this matrix, rank of A, rank of A means number of non-zero rows basically in Gauss Jordan or Gauss elimination form. So this is going to be 2 only, right? But if you see the rank of the entire matrix is 3. So this system is also not having a solution actually, right? But anyway, let us move further. So what had happened? You got 0 pivot entry. So what had happened? Now next job is to make above 0 to the pivot entry. So pivot entry is only in the second column. So we have made the 0 using suitable elementary row operation. And then it's just, this is just simply you are going to add R2, R1 plus R2 you are going to do, so that it becomes 0, and then remaining are going to be changed. Okay, so now in this case the last row tells us that the system has no solution for alpha, beta, gamma. You can also see from the last equation, alpha times of 0 plus beta times of 0 plus gamma times of 0 is equal to minus 33 by 5. It means 0 is equal to minus 33 by 5, which is absurd result, right? Which is not true at all. Therefore, system has no solution. It means that what we have concluded, the vector, this does not belongs to the row space of the given matrix A, right? And we see, we also see from the last matrix that the linear combination, the last matrix means this matrix, you see that these two are the linear combination of the third vector. Therefore third vector got into the dependent actually. And then you see here this vector is a linear combination of these two vectors. That means the third vector is a dependent on these two vectors, right? And if see the last column has no pivot, it means the corresponding column has free entries, right? So now there is another important theorem. Let us have a look on this theorem. Suppose the matrices A and B are row equivalent, then the row space of A is equal to the row space of B. This is a very, very important result. Very, very important result. So proof is very trivial. Let us see how to prove that. Right? Row equivalent means two matrices are row equivalent. Two matrices are equivalent means the solution set of A matrix has the solution set same as the solution set of B matrix, right? So A is being obtained after applying suitable B can be obtained after applying suitable elementary operation on A, and A can be obtained here if you see A. So elementary row operation if I do on B, if I say finite number, finite means I'm going to apply elementary row operation in number of operations are finite here I mean to say, and I got a B matrix. So if I want to get back B matrix to A matrix, I have to use the same elementary row operation in reverse order, right? So these two matrices, the solutions of two systems are having the same solution, right? So they are called as A is equivalent to B matrix. Okay. So here proof. We prove that if the matrix B is obtained by applying a single elementary row operation to the matrix A, then the row space of B is equal to row space of A. First, we are going to do with the finite number of operations, and we know three elementary row operations. So we are going to apply every operation single time. Then we generalize it. Okay. This is the whole idea of proof. So what we can do, we assume that A is of M by N matrix. Let us denote the rows of A as R1, R2, and so on Rm. Okay. So now if you see here, case 1, B is got from A by applying the type 1 elementary operation, the row operation, right? Type 1 elementary row operation means we can, we can multiply any row by a non-zero suitable scalar, by a non-zero scalar, I can say. So say B is got by multiplying the ith row. Assume ith row was multiplied by C and non-constant C, non-zero constant C. So we are going to represent the new vectors of row vectors of B will look like R1 as it is, no change, no change, Ri minus 1, no change. But yes, Ri we are going to multiply by C times first elementary row operation, right? And then remaining are same. Okay. Now what had happened is, if a vector U is in the row space of B, then any vector, as you know, if any vector is in the row space, from the previous two example, if you have seen, any vector is in the row space, it means that that vector can be written as the linear combination of the row space of row vectors of the given matrix. So you know row of the B matrix is R1, R2, and so on, C times of Ri and Ri plus 1 and so on, Rn. Okay. So U can be written as the linear combination of them for some scalars. Okay, alpha 1, alpha 2, alpha n. This is coming from the definition also, definition of row space. Okay, and you can write it like C times alpha I and Ri using the property of the vectors, and hence this is Ci is another new scalar, right, which is exactly the linear combination of your row space of A, right? It means that thus the row space of B belongs to row space of A, right? Now A can be got from B by applying type 1 elementary row operation, namely multiplying the ith row of B by a non-zero scalar, right? Just as I told you, reverse in order, right? Non-zero C, if you have multiplied, then you have to do division while converting back elementary row operation to receive A from B, right? Reverse order, 1 by C. And hence the row space of A is contained in row space of B. And similarly, we can say that row space of A equal to row space of B. Now let us take the next case. Let the matrix B is got by A by applying the single type second elementary row operation, namely we are going to add I row C times to the J row where C is non-zero, right? So the ith row will be affected like this, Ri plus C times of J row. And as you know, any vector U, similar story, any vector can be written as a linear combination of the row space of row vectors of the given matrix. Then we are going to write it, and using the property, we can write it like this. Okay. And which is nothing but the sum linear combinations of the vectors alpha 1, alpha 2, and so on. Alpha j plus C times alpha I is again a scalar, right? So hence this is hence is in the row space of A. So what we can conclude, row space of B contained in row space of A. And now if you see, we can do the reverse by subtracting C times in row J. So this is the reverse operation we are doing, right? So this will give you the same space. So row space of A contain row space of B. It means row space of A equal to row space of B, or row space of B equal to row space of A, right? If I want to say A is equal to B, so what am I going to say? If I say A is contained in B and B is contained in A, which implies these together implies A is contained in B, right? The same story we are doing here. Third case, Let the matrix B be got from applying the single elementary three operations, right? Elementary row operation by namely interchanging the rows, right? Then hence what had happened? The rows of B are the same as the rows of A in but only in different order, right? So now since the vector addition is commutative and associative, and any vector which is a linear combination of the rows of A is also the linear combination of rows of B and vice versa. That is, any vector in the row space of A is also in the row space of B and vice versa. This is a conclusion, right? Thus, the row space of B is equal to row space of A. Now, thus the row space does not change if we apply single elementary row operation, right? As we have seen, single elementary row operation we have applied in each three different cases, but row space does not change, right? And so does not change if we apply any finite number of elementary row operation also, right? It concludes that if you apply finite number of elementary row operation on a given matrix A, and if you get another matrix B, then row space does not change. Or we can say that row equivalent matrices has same row space. This is the proof. Thank you.